Hello, 1C class. Today's a Sunday, but I want to start my lesson so that way you guys can have it tomorrow morning. Today is a very, very important lesson. We're going to start learn some of the application problems. So this is for March 23. Okay, you don't need to look at it until tomorrow. But if you want to start early, you can start today. So this is for 13.6. On 13.6, we're going to learn a very, very important concept. The first one we're going to learn is called a gradient. Gradient may use a notation del f for a function z equal to f x y. If your function is some other notation here, then you change this also. This is with the triangle, upside down triangle, we read as a del. And del f, so because I use f here, so del f is a vector perpendicular to the level curve. We know what level curve is. It's when we chop the surface, okay, we have a outline, it's kind of like an outline of the chopping part. So I will have an example here. So that means that del f is a normal vector. Now watch this very careful. This is a normal vector, so that means that this vector is perpendicular to the surface. The formula for del f for two dimensions is a fx. It's a two variables, fx and fy. So it's a partial to x, partial to y. It's a vector, so therefore it's a common between. Now, so what does it look like in example? So let's say this is a hill here, okay, and there's a three-level curve. That means you can chop it, okay. So I just chop three of them. And let's say there's a point P here, okay. You are going up to this direction, okay, you're going up, so I use a U as a vector. Now this U has a meaning there, I'll tell you what is it. And this, I'm going up this direction, so I use a U as a vector, the direction, the movement. And if I'm going to look at the top view, okay, I'm going to look at the top view here, okay, the top view of the hill, so look at this one. So it's my second one, okay, the second circle, the second contour. And this is a tangent line here, and then the gradients are right here. This is a level curve, right? This is a level curve. So this is a gradient as a perpendicular to this level curve. So perpendicular tangent line here, okay? So, and then if you want to, you can draw a 90-degree angle. And when you're going uphill, okay, I'm using positive. When I'm going downhill, I use a negative. Now the second, so why do you want to learn gradient? Okay, I'll tell you that later on. But second concept will be directional derivatives. Directional derivative means you want to find the slope or find the derivative on the direction you want to find. So remember that last session we learned to find the derivative on x or derivative on y only. But now you can find the derivative on any direction you want. Okay, so now I want to find derivative for the direction u. Okay, so it's a one direction for u here. I say, hey, what's the slope for this hill here? Okay, and so derivative, it means a slope. It means a rate of change. Okay, this is all the same thing. Okay, on the direction of u. Okay, directional derivative means to find the slope on the direction of u. We use a notation called duf. It means the derivative of f on the direction u. That's what they mean. Now u has to be a unit vector, okay? It means you need to normalize it. Why do you want to use unit vector? It's the same concept. We want it to be standardized, okay? So we don't want to have so many length of unit vector. We want to have a length of a scale for one like that. So what is the directional derivative with a relationship with del f? Okay, so here's basically what is it. Okay, if your del f here, your directional derivative here, so means that your del f on this part is a perpendicular level curve, is about right here, perpendicular to this one. So it's about this perpendicular to here. Okay, we couldn't see it well because it's three dimensions. You will see it perpendicular to this curve. So that's my, okay, del f. And then directional derivative is a del f project on u, because these ones are changing. Okay, these are changing. keep changing because it's perpendicular level curve. So this one can, when you keep going, it's still perpendicular. Okay, if you're going this direction on the YZ direction, on YZ plane, it's still perpendicular to the level curve. So I put it on here. Okay, I said since this one here, okay, it can change on the YZ plane. That's my U, so I just move like this way. Okay, move like this. Now when this del F is perpendicular to U, when it's perpendicular to U, it actually equals 0. Okay, there's no slope here. No slope. When they're perpendicular, there's no slope. And that's because their angle is 90 degrees, so cosine 90 degrees equals 0. That's the reason we use that the slope, the angle formula. And then this is equal to 0. And then you can see that as they move down here, okay, the del F move down. And then if I want to move to here, I draw a line. Okay, this quantity here, this quantity, the length of here, is the slope. It's the slope of the directional derivative on U. Okay, so therefore we also call directional derivative on F is a scalar. Scalar, it's not a vector, it's a scalar. Okay, it's just a number, it's a slope. It's a scalar projection of del F on U. It's a scalar. Okay, it's a scalar. Now this is be careful. Scalar means it's a number. It's a real number, okay, on U. Okay, it's a del F on U. And you can see that as you move, now as you keep moving onto this direction, and your scalar gets longer, that right? It's longer before it was here, now become here. By the time it all the way to the bottom here, now overlap the U, you get the maximum slope. Okay, maximum derivative. Once the del F overlap the U, you get the maximum rate of change or maximum slope. Rate of change is still the same. Now, if I'm going to rotate the other side, look at what happened. When I rotate the other side, my DUF is a negative. Okay, so your slope start decrease. When you decrease when you're on the opposite of a U, you decrease the most. So that means like for my U is here. Okay, when I go up here, I'm same direction, so the slope is the maximum change. Okay, you can see it's very steep going up. But when I go down, when I go back down the hill, I'm opposite of the U here. My directional vector is still the same. You still direct up. But when you go back down, what happened? When you're downhill, you slice down. So let's say you fall, slice off. And then what happened? You decrease fast. Your slope decreases fast. Okay? So that's how it goes for directional derivative. Now there's a lot of things going on with directional derivative. So I have to erase here to show you. If in class I have more to say, but on the video I couldn't put too much information in the half hour. So that's basically the key, okay? So now we're going to do the formula for directional derivative. Then I'm going to tell you why do we have the line gradient, what's the benefit of it. You can see some of the benefit already, okay? The gradient and U, there's some relationship there. So this is content number 2, formula for directional derivative. And there's 2 formulas, okay? The first formula is if number 1, if theta is given, where's my theta then? Okay, here is your theta. Your theta is the angle. Is the angle between the U. So let me just draw this quickly. Okay, if I use the x, y, z here. Okay, here's a vector, directional derivative U, and this is my theta. Okay, so theta is a angle between this directional derivative and x, okay, project on the xy plane, and that create this theta. So if theta is a given, and the formula will be equal to fx cosine theta plus fy sine theta. So that's number one. Number two, now we don't usually give a theta. Most of the time we are giving u. If this is given, so they project the u from the surface onto xy plane. That's how they create the theta, okay? If u is given to you, okay, the formula we're going to use the directional derivative formula will be equal to del f. Now this is dots unit vector. Unit vector, now that's a dot product here. Okay, that's a unit vector. Okay, so what's the purpose about learning directional derivative? Then we can find the slope in any direction we want. So that's the purpose of it. And that's very important because if you want to know the slope in any direction we want it, it's not just on x or on y or on z, okay? We want it to be in any direction we want. But the purpose of a gradient, okay, learning gradient, okay, and let's say I put this gradient as z is equal to fxy, so the gradient be del f, okay. So what's the purpose about learning this gradient? So first purpose is to maximize or minimize the directional derivative on direction of u, okay? The maximize derivative of this one is on the same direction when the directional derivative is on the same direction del f, you get the maximized slope, and the slope will be this formula. So that's the maximized slope. Okay, it's the same length of the gradient. I erase the picture. So when it's on the same length of gradient, okay. So remember earlier I have a u here, and the del f coming down. Okay, when del f here, you get the maximum slope. Okay, and the length of that is your maximum slope. And we also get the minimizer. Okay, the minimizer is negative del f. So that's number one. Number two, okay, what's the number two reason? That way now we no longer need to find the cross product for a surface, okay? We no longer need to find the cross product. So number two, we can find the equation of a tangent plane to the surface. See, usually when we have to find the equation of plane, we need to find the cross product. Then we find the normal vector that's perpendicular to the plane, right? But if you're given a surface, it's very hard for us to find two vectors to cross it. So now we just need to find the gradient of the surface, and that will be the vector perpendicular to the plane. Then from there we can find the tangent plane, the equation of tangent plane. So that is the purpose of it. So that's the two purpose. But these will be 13.7, and now in 13.6, we're going to do some example, okay? The first example we're going to do is to learn how to find the gradient, directional derivative. So this is problem number 4. We are given a function fxy equal to y over x plus y. And there's a point P is at the point 3, 0. And we are given theta is equal to pi over 6, negative pi over 6, sorry, negative pi over 6. They said find this one. Okay, well, I gave you two formula earlier, right? So the first formula, that's what we're going to use. Okay, the first formula is equal to fx cosine theta plus fy sine theta. So we need to find the partial for x first, okay? So partial for x is equal to, so there's a negative y over x plus y squared. And chain rule the x but just 1 and cosine theta. Fy, that's the quotient rule, so y prime first. So that's a 1, so your x plus y, subtract, keep the y, and then take the derivative here, so that's a 0, that's a 1, so that's a y. And then x plus y squared, and then sine theta. Put the information inside. Y is equal to 0, and so that's a 0 here, right? So this whole thing is a 0, so that's kind of nice because it's 0 times anything that's a 0. Plus these two cancel. X go inside the 3, x equals 3 plus 0 square, and sine negative power 6. Let's see, that will be 3 squared, so that's a 1 over 3. Sine negative same as a negative sine. Sine power 6 is 13 degrees, so it's a 1/2. It comes like a negative 1 over 6. So the slope is negative, means you're going downhill, okay? That's what negative means here. So that's not too bad, right? So make sure you guys I want you to look at this lesson before Wednesday when I do the office hours, so you can ask me any question then, because I cannot give out all the information on the 30 minutes video. Next problem, number 12. We are given a surface function equal to cosine x plus y, and we're given 2 points this time, okay? Point P is 0 to pi, and point Q is a power 2 to 0. So the first is we're going to find our gradient, okay? Let's find the gradient first. The gradient is equal to, because we are not given theta, okay? Actually, we're given a u. There's a u here, but I haven't found it yet. Okay, there's a vector between 2 points, right? I want to find the gradient first. I'll tell you why. And that's equal to f of x is equal to negative sine x plus y. By the way, that's very likely I probably wouldn't test you on 11.1 and 2 anymore because it's a chapter 11, chapter 12, because the situation. I probably start testing on chapter 13, 14, and 15 because these are the most important lessons. So if we can go back in May first, then we're going to have our first exam. We'll be on 13 and maybe a portion 14. Okay, so make sure you keep on it because 13, 14, 15, that's what 1C is about. So most important lessons on these 3 chapters. and chapter 11, 12, with some of the information we use it, but then we will use in this problem also. So therefore you wouldn't miss it. So you wouldn't forget about it. And so f of x is negative sine xy, and the fy will also negative sine xy. Okay, and then you can use either one of the number to put it inside. And I put in 0 pi. You can put in any number, okay? I'll tell you why I like to find del f first. And that gives me what happened here. This is negative sine pi. Negative sine pi. Negative sine pi, cosine pi is equal to 0, so 0. After I see my gradient is 0, I don't need to find my u. The reason 0 dots u, okay, that means the gradient dots u is a gradient dots the pq vector. It's just equal to 0. So I don't need to take my time to do that. So I always find the gradient first, okay? If you're given 2 points, I would definitely find the gradient first. So that tells you this is slope is equal to 0, okay, at these 2 points, either point, okay? So at the point for 0 to pi, power 2 to 0, they all get 0 as a slope, means it's a horizontal line. It is a horizontal line when the slope is equal to 0. So that's number 12. So when you finish the problem, I want you to think about what this answer means to you. No, don't just get the answer out. Think about it. 0 means a horizontal tangent line. Okay, horizontal tangent line is on these 2 points. The next problem is number 24. We are given function x, y, z is equal to xy plus yz plus sz. And this lesson I probably did break 2 videos, so I'm going to finish this problem, that 1 video, okay? Then we're going to do another one. So now, get the gradient. We are given 2 points also. Point P is 1, 2, minus 1. Point Q is, no point Q. We are given a directional vector actually. Sorry about that. We get 2, 1, and negative 1. We are given a directional vector. They said find this one. Okay, the directional derivative on the direction of v. So get the gradient first. See if we're gonna get 0. And are we that lucky always get 0? Probably not. So that's equal to f of x, that's a y here. No x, so 0, that's a z. Fy is an x plus z. Fz is equal to y plus x. And we put the point inside. Okay, and that's equal to, okay, y plus z, so that means y plus z, so it's a 0. And the second number is, it's a y plus z, sorry, y plus z. Yeah, y plus, this one, sorry, I look at this one, so it's not 0. Y plus z, so it's 1, okay. And the x plus z, I have to look at it, x plus z, that's a 0. And the last one is y plus x is a 3. So 1, 0, 3. Not 0, so therefore we need to find this one. Well, find the length first and make sure if it's a unit vector or not. the length of V is equal to 2 squared plus 1 squared plus a negative 1 squared. And which is equal to what? 6. This is not equal to 1, so that means you didn't normalize it, okay? To normalize it, just take the vector divided by the length of vector. And that's equal to 2, 1, negative 1 over square root 6. And if you want, you can put it inside. So 2 square root 6, 1 square root 6, and negative 1 over square root 6. And then we're going to dot them together. Hey, let me write one more thing. Okay, so people know that you are in the direction for V. Direction of V. Okay, make sure you write that. Now that cannot skip. So that's equal to okay, and that's equal to del F is equal to 103 dots 2 over square root 6, 1 over square root 6, negative 1 over square root 6. It comes out equal to 2 over square root 6, that's a 0, minus 3, oh, sorry about my writing. So equal negative 1 over square root 6. Sorry about that, it's a little bit small. Again, we get a negative slope, okay? And maybe I do one more example. The last example might have to break into the second video because that one's very long. The last one's kind of long. Let's try another one. Okay, now here, this one, they ask you a little bit differently. Okay, so now you know how to find the gradient and you know how to find the directional derivative. So this one is, they say find the maximum directional derivative. Maximum, where's the maximum directional derivative? Number 34. Okay, you are given a function, the surface function is equal, oh, sorry about that, that's a ln q x squared plus y squared at the point 1 and 2. Okay, they said find the here's what they want to do. They said find the maximum value of the directional derivative. Now you notice that they didn't even give you the directional derivative here. They didn't give you the directional vector. They don't have to, because the directional derivative, the maximum directional derivative, the maximum. I make a mistake, huh? M-A-S-I, maximum. If I make a, feel free to correct me, okay? If I make a mistake on spelling. So the maximum directional derivative does not require to know what is the directional vector. Remember that? All they need to know is we know that they come down here, they overlap. As long as they overlap, that will be your maximum. Okay, that's the maximum. Okay, which is equal to, like, remember the maximum of this one. Okay, the formula is equal to what? Okay, it's just the length of the del F. So now we just need to find out what is the gradient for that. So we need to find del G. Okay, I want to use this one. So to find del G, I'm going to simplify this function first. Okay, I'm going to make this a 1/3 in the front. Remember in class I told you guys It's just easy when you take the partial derivative, okay? So g of x, yeah, just do one step, okay? Del g equal g of x, g of y. And g of x is equal to 1/3 1 over x squared plus y squared, and then 2x. And then you can see the same format for the x and y, so therefore will be the second be the same. So this is for the first one. Now we're just going to put the points inside. When you put the points inside, so you got to write it, okay? Cannot be lazy on this part. And when I put the 1 inside and I calculate to save time, it's just equal 2 over 15. And another one's equal 4 over 15. Okay. Now I just need to take the length of that. Okay, so that'd be 4 over 15 squared plus 16 over 15 squared. And then I calculate out is equal to 2 square root of 5 over 15. So is the maximum slope you can get, okay? It's the maximum slope you can get. So that wraps up for part 1 for my 13.6, and then I'm going to go part 2. I just need to do one example on part 2.